Hi everyone, it's very welcome to attend the CMSC seminar. So today we will have Vasil Rokaj from Harvard ITEM to talk about the controlling quantum matter with quantum cavity fields. Yeah, please start. Yeah.
Yes, thanks a lot, G. Thanks for introducing me and for inviting me and giving me the opportunity to present my work at CMSA at your seminar. So as the title of my talk says, so today I'm going to present to you how we can control quantum matter with quantum cavity fields. And before we go into the actual topic, let me try to introduce and motivate why this work is relevant and where does it come from? What are the stimuli for that? So this work is motivated by the advances in cavity quantum electrodynamics and strong light matter interactions, where what happens is, like, typically in free space, the interaction between light and matter, it is weak, and because it's perturbative, it is determined by the fine structure constant, which is a small number. So you can treat interaction between photons and matter in free space perturbatively. But now in a cavity setup, it means that you have essentially something like two mirrors in which the vacuum field fluctuates. In this setting, because of the modification of the electromagnetic environment and the enhancement of the field fluctuations and the enhancement of the field strength, the interaction between light and matter becomes strong. And this strong coupling leads to the formation of hybrid quasiparticles between light and matter, which are known as polaritons. And what has been shown is that the formation of polaritons and this strong coupling between light and matter leads to the modification of properties of matter. Let me also just say that you can, anytime you can interrupt me with a question. I mean, it's quite nice actually to get some feedback from you and whatever questions you have while I present. Okay, so feel free to ask me anytime. And as I was saying, so the polaritons have been explored now, both in condensed matter, but also in chemistry, and particularly in condensed matter. One thing that has happened is that experimentalists have been able to couple 2D electron gases to cavities. So here, what I mean by that is like Landau levels in 2D electron gases. So we have a 2D material in a homogeneous magnetic field, and we couple it to the cavity. And what you can see in this plot here is you can see this large avoided crossing, the Rabi splitting within the Landau level excitation and the cavity excitation. And most interestingly, what has happened as well is that people have now been able to study transport in these settings. And what it has been shown is that both, for example, the magnetotransport of the Shubnikov-de Haas oscillations in quantum Hall systems can be affected by vacuum field fluctuations, but also the quantum Hall transport can be affected. And there was a talk a few weeks ago by Jérôme Feist, who is leading this group doing these really exciting experiments, which you can find also on YouTube. So I will not talk really much more on this, but this is a really great reference. And now on the chemistry side, experimentalists have been able to put inside cavities, so between two mirrors, large ensembles of molecules. And what it has been reported is that chemical properties and chemical reactions can be modified by strong coupling to the light field, to the cavity field. And it has been shown, for example, that particular chemical reactions, in some cases, they speed up, or in other cases, they get suppressed and do not happen. And also, it has been shown that charge and energy transfer can be modified by coupling to the cavity vacuum field. And the key experimental features that show up in these experiments, which are still not fully understood, is the fact that these chemical processes that get modified, these are ground state reactions that get modified. So there is a modification of the ground state that happens in these large ensembles of molecules. And also that these modifications happen when the vibrational states that the cavity couples to is in resonance with this vibrational excitation. So the light excitation and the vibrational excitation of the molecule is in resonance. And a key aspect that shows up as well is collectivity. So what I mean by that is that you put more and more numbers of molecules in the cavity, and then you see these phenomena to show up. So there is some sort of collective behavior that shows up in such systems, which is hypothesized to be responsible for these modifications in chemical properties and reactions. And what I would like to do today is to show you two examples to relatively simple analytically solvable models, in which on the one hand side, we can see that conduction properties of an electron gas can be modified by coupling to a cavity. So this I will show to you by using the paradigmatic Sommerfeld model of the free electron gas. We will couple this system into a cavity. We will see how the conduction of this system gets modified by the cavity. And this is an analytically solvable system on which we can study the ground state properties thoroughly. And what we will see that the importance of the A squared term, the diamagnetic interaction from the cavity field that stabilizes this system and prevents the fact that to have a superradiant phase transition. And for those who are not familiar with this term, the superradiant phase transition, this is a phase that has been predicted by Hepp and Libby in the 70s to happen if you have an ensemble of two-level systems. So if you have the decay model, which is like an ensemble of two-level systems, you couple them coherently to a cavity, and then you see that eventually the ground state of the system gets occupied by a macroscopic amount of photons. So you have a photon condensation.
Yeah, let me ask one question. So you mentioned in the chemistry slides, the cavity modify the ground state properties. So here the ground state means the ground state, Lewis energy state of a molecule or a lot of molecules. So can you clarify the difference between the ground state in chemistry and the ground state in condensed matter?
Yes, so typically molecular processes, as you correctly said, are processes which happen locally at one molecule. But here in this setting, what the experimentalists say, this is of course still not fully understood, but you can also find nice reviews that discuss this, that what they say that happens is that the collective ground state of this large ensemble of molecules gets modified. That's what they say. This is why I highlight here collectivity, that you have this collective state that gets modified. So it's not just about the individual molecular ground state.
Mm-hmm. Okay? So I can think of this system as a liquid of
exactly.
Mm-hmm.
Exactly. It's these molecules are exactly in the liquid phase, and they are also in solvents. In a solvent, they are in solution.
Mm-hmm.
Okay, so they are not in the gas phase.
I see. So second question is, when you see the A squared term in the next slides. So is there any realistic way or experimental way to kill the A squared term to get superradiant transitions?
Yes, there have been some proposals, and there is a quite large literature about this, but always all of these proposals there have been counter demonstrations and no-go theorems in which they say that always some kind of interaction has not been taken into account by this proposal. So this has become a little bit of a debate in the community. So, so far there has not been an unambiguous, let's say, at least to my knowledge, there has not been an unambiguous demonstration that you can really go around these no-go theorems.
So that is to say the superradiant phase is not yet experimentally realized.
It's not at all. It's not. Experimentally, it's not realized. Only in some driven systems, in cold atoms, they have seen something like that, but the system has been under driving and it has been open. So there has always been an interaction with the environment. But these superradiant phase transitions, like the one in the decay model, these are really in the ground state of the system in equilibrium without any driving or sort of thermalization from an environment. Okay. Okay. So it's really isolated ground state phase transition. And now, in connection more to the connection to more of the molecular chemistry side, the second thing that I would like to show you, again with a relatively simple model, is that if we have many particles in a harmonic trap, so in a harmonic oscillator, you can think of that like electrons in a trap or ions. Probably ions is the best way to think about them. So like cold ions in a harmonic trap, and you couple them to the cavity. In this setting, what I will show you is that really indeed polaritons emerge, so hybrid quasiparticles between light and matter, between the ions and the cavity photons emerge. And really in this setting, there is a modification in the ground state, and there is a collective behavior in the system. So the more particles you put in, you really see a larger effect in the modification of the ground state. And also another key result that shows up in this model is that the modification of the ground state becomes maximal when we are in resonance with a cavity. Okay. So before I go into details, let me just first introduce the setting in which I work with, which is non-relativistic quantum electrodynamics. So non-relativistic quantum electrodynamics is a theory that describes like the interaction of charged particles, which are slowly moving. They are not in high relativistic velocities, and they couple to the photon field. And this theory is described by the Pauli-Fierz Hamiltonian or minimal coupling Hamiltonian. Here it is quantized in the Coulomb gauge. And what we have is the momenta of the charged particles, and they are minimally coupled they can be coupled both to an external classical field, like a magnetic field or an electric field, which does transport, for example, to your system. But we also have the quantized field A hat, which this now models our quantized modes of the cavity. And of course, we have the standard classical external potentials, which, for example, model the ions in a solid. We have the two-body interaction between the electrons and the energy of the electromagnetic field, which is the sum of harmonic oscillators, with the sum going over all the frequencies and the polarizations in the field. And here is the expression for the photon field, the quantized photon field, where we have annihilation and creation operators. These are the bosonic operators which create photons. And typically in this setting of cavity QED, we work in what is called the long wavelength limit, or the dipole approximation, in which the spatial variation of the electromagnetic field is not taken into account. So what it is assumed here is that the spatial variation of the field, that the wavelength of the field is much larger than the size of the matter system. So you can essentially drop these plane waves. Okay, you can take them to be approximately equal to 1. Okay. Is there maybe some question here, or no?
So this is to say k equals 0?
This is approximately k equals 0. Approximately, yes. For an atom, this is very good approximation. And for a 2D material, if you only consider the perpendicular mode, the kappa z mode, it's also a good approximation. But of course, if you think about the in-plane modes, kappa x and kappa y, then this is not good for a 2D material. But mostly I am thinking about here the perpendicular modes with respect to the 2D material. Okay. So let me come now to the first part of my talk, which has to do with the free electron gas in cavity QED. And the system that we're considering is the one that you see here in this figure. I have a piece of a metal. It's a 2D slab of a material, and now we put it between two cavity mirrors. The distance between the cavity mirrors is Lz, and we have this cavity field. And the motivation for this system, I mean, as I told you, experimentally study macroscopic condensed matter systems coupled to cavities, but so far there have been no analytically solvable models for extended condensed matter macroscopic systems coupled to the photon field. And we want to fill this gap by looking at the Sommerfeld model coupled to the cavity. And the assumptions that we take to study these models are the standard ones of the Sommerfeld model, where the external potential of the system is 0. There are no Coulomb interactions. And here, as a starting point, I will only show you what happens when we have one mode in our system. So a single frequency of the cavity, the perpendicular one, kappa z mode. But in our paper, I have also studied the more generic many mode case, but today I will only stick to the single frequency, single mode case. So the Hamiltonian of the system is the one shown here. So we have the momenta of the particles of the electrons, and they are coupled to the photon field, which is given in terms of annihilation and creation operators, and the field now is already in the dipole approximation or long wavelength limit, where it is homogeneous. And here we have, of course, the energy of this harmonic oscillator, which oscillates with frequency omega. And we have the two polarizations, which are in the in-plane, because as I said, I am taking into account the kappa z momentum, so the polarizations are perpendicular to it, and they are in the in-plane of the material. And the nice thing about this model is that it is analytically solvable. And let me take a couple of slides to explain you how this can happen. So if you expand the Hamiltonian, what comes out is that you have the diamagnetic term, the A squared term, which gets this n amplification because you have to sum n times over it. And you also have this bilinear coupling between the photon field and the momenta, and of course, the kinetic energy of the particles. And the first step is to diagonalize or absorb the A squared term by performing a Bogoliubov transformation in which the cavity mode gets dressed by this diamagnetic frequency, which comes really from the A squared term. And this diamagnetic frequency, it's essentially the electron density in the cavity, because this is the 2D density, and this is the distance between the cavity mirrors. So you get from the A squared term, you get this renormalization of the bare cavity mode, which is imprinted also in the transformation for these dressed photonic operators. And now, once you have done that, you have absorbed the A squared term, and you have a diagonal part for your mode, but you still have this bilinear coupling. And now the key thing is that this system has translational symmetry. So the momenta of the electrons are good conserved quantum numbers, and this means that the electronic eigenstates are plane waves. So what we can do is just essentially just apply the Hamiltonian H on the plane waves, which are the eigenstates of the electronic system. And then what you have is first the kinetic energy of the electrons. And of course, here we still have these renormalized bosonic operators, and we have this bilinear coupling. Let me also just say that the A field, also in the new basis, in the B operators, in the renormalized ones, it's also a linear combination of B and B dagger. Okay. And since I see there is a raised hand by Pavel. So
yes, could you tell you mentioned that there is a translational invariance in plane, but doesn't that mean that you should also couple to all kind of plane wave-like modes of light? So basically, that A has a modulation along K in plane, and that will be some kind of continuous spectrum.
Yes. So as I said here, I only have one mode of the cavity, and this is the perpendicular one to the material. So I'm only taking the kappa Z momentum, which is perpendicular to the material. Okay. So now if you would think of this plane wave modulation, you can think that now the wavelength, it is larger than the actual thickness of this 2D material. So I'm only taking really this perpendicular mode. If I would include also the in-plane modes, so the photonic modes, which are in kappa X and kappa Y in the in-plane, then this would actually break translational symmetry. But as long as I am taking into account only the perpendicular one, then there is no problem. So translational symmetry in the in-plane is still preserved.
Is there any physical reason that you shouldn't consider this kappa X, kappa Y modes, or
no, there is no.
Okay.
No, there is no physical reason to not consider them. Of course, it is unclear in the experiments what is actually, which of these modes are, whether all of them are contributing or whether some of them are contributing. Okay. As I said in the paper, we're actually taking into account also the multiple of modes, but here I'm only restricting my discussion to this one perpendicular kappa Z mode.
Okay, thank you.
So this is just in order to get essentially an analytically solvable model of a condensed matter system in the large N limit, okay, where we can go to the thermodynamic limit, okay? And yes, where was I? Yes, so I was at this point. So the electronic eigenstates are plane waves, and then we can essentially apply the Hamiltonian on these plane waves, and this is what we get. So we have this still bilinear coupling between the momenta and the A field, and this is also easy to diagonalize by doing a coherent shift transformation. So what I'm doing here is I'm shifting the B operators, the dressed bosonic operators, by the total momentum in the system. So capital K is the sum of the single particle momenta. And once you have done that, then essentially you have solved your problem. Because what this does, what this shift transformation, what it does, it introduces a new term with respect to the momenta of the electrons. So what I'm talking about is that then, once you have done this transformation, you get the exact eigenspectrum of the system. And let me guide you through this equation. So first, we have the kinetic energy of the particles. Here is, of course, the energy spectrum of the two bosonic modes, the renormalized modes, one for each polarization. And then we have this negative term, which comes from this displacement shift that I did on the bosonic operators. And this is the part which comes from the light-matter interaction. Okay, let me say that this is a term which is negative and depends on the quadrature of the total momentum of the system. So it depends essentially on the collective momentum of the system, on the center of mass momentum. Okay, And the coupling constant that determines what is the strength of this term is this gamma parameter, which is the ratio between the diamagnetic frequency and the renormalized frequency of the cavity mode. And this has an upper bound. And this upper bound will be important for what we see next, for the ground state of the system, the relation to the A-squared term, but also for the conduction properties of the system. And the key thing that I would like to say is that if you expand this quadratic term, which depends on the total momentum, what you will see is that you have an all-to-all electron interaction because the momentum of each electron couples to the momentum of all the others. So this is a photon-mediated interaction that you get from the cavity. And the first question we want to ask is what is actually the ground state of the system? So what I mean by that is that we need now, in order to find the ground state, of course, for the bosons, it's clear, just it has to be at the 0th level, but now we have to minimize this energy expression in K-space in order to find how the electrons occupy the K-space. So to do so, what we did is like to consider a generic distribution in K-space where it has an arbitrary origin Q and an arbitrary shape D. And now in the thermodynamic limit, these sums turn into integrals, and you can compute these integrals with respect to the shape and the origin of the surface. And what we found actually is that the ground state, the one that optimizes this energy spectrum, is actually the standard Fermi sphere. So the ground state of the system does not, of the electronic system, in this case, does not get modified. You just have the standard 2D Fermi sphere. And this is a tensor product now with the vacuum state of these bosonic renormalized operators. So from the matter side, this is essentially a trivial state. But the question is this actually a trivial state overall? So are there maybe on the photonic side non-trivial phenomena happening? And to answer this, what we did is like, yes, of course.
So here you actually turn off the interaction, right?
No, I'm not turning off the interaction. I'm not turning off the interaction.
The Coulomb interaction. Coulomb interaction.
The Coulomb, yeah, there is no Coulomb interaction here. There is no Coulomb interaction.
So my question is, if you turn on Coulomb interaction, what happens to your ground state?
So because this is a work that started quite long ago, so the Coulomb interaction cannot actually change this result.
You mean the ground state function?
So the ground state, of course, will change. But what I want to say is that the Coulomb interaction is not really important for the light matter part. So what I mean by that is because the field is homogeneous, the cavity field does not see the correlation between the particles because the correlations depend only on relative distances. While the cavity field here, because the system is homogeneous, sees only the collective motion of the system.
Okay. I see.
That is.
So you mean the Coulomb interaction, including Coulomb interaction, the ground state wave function remains in such a structure as that
exactly
for the product of fermion part and the boson part as a
exactly
changes the electron. Okay.
Exactly. So the bosons here cannot change really the ground state, even if you include the Coulomb, because the photons here are really homogeneous, so they do not see the correlations. Okay. But when we wrote this paper, we actually didn't really know that. But in any case,
but
we grow
the Fermi liquid. It has a Lagrange theorem. It tells you that the size of the Fermi surface is invariant, even though you have interactions. So it might be interesting to ask if you have a inhomogeneous cavity that's light matter coupled. What happens to the Lagrange theorem was to the size?
I completely agree with you. For the homogeneous electron gas, the really interesting case is to go beyond this homogeneous approximation, where you can really have exchange of momentum between the photons and the electrons. This is a really interesting case. I agree with you. But let me come back now to the properties of this ground state. And the one thing we want to see is like whether there's something interesting to it or this is completely trivial. And what is interesting is that despite the fact that the fermionic part has not changed, the ground state photon occupation of the system is non-trivial. So what I mean by that is that we compute now the photon occupation in this ground state, and what we found because of this renormalization of the cavity field, there is actually a non-zero photon population, which depends on the particle number or on the electron density. But as you can see here, I have a proportionality to the density. So this means that this electron photon ground state, which is dressed with photons, does not have an infinite photon population, but the amount of photons, it is finite. So it doesn't grow with a particle, but it grows with a density, where the density is not an extensive quantity, okay? And this is in contrast to the decay model, in which, because of not taking into account the A squared term, what they find is an infinite photon occupation. So if you would compute the photon population per particle is non-zero. While in this system here, because of the A squared term, if you compute the photon population per particle in the thermodynamic limit, it is essentially zero, okay? It is finite, but it is not a macroscopic photon occupation. And now, the next thing I would like to discuss to you, what is the full phase diagram of the system and what is really the importance of this A squared term. So what I mean by that now, that here I told you what happens as long as my gamma, the coupling, this ratio, it is from 0 to 1. But now we can also imagine the situation that I artificially play around with gamma and see what happens to the system. And the interesting point is that when gamma reaches the value of 1, what happens is that the positive and the negative contributions that I had previously in my energy spectrum, they essentially balance each other. And what happens is that the ground state of the system becomes infinitely degenerate with respect to shifts in the 2D plane in K-space. So what I mean by that is that all 2D Fermi spheres in K-space, irrespective of their origin, they have exactly the same ground state energy. So there is an infinite degeneracy that happens if gamma was allowed to reach unity, okay? And this is similar also to the Landau levels, where they're also infinitely degenerate in the ground state. This is a nice similarity that comes up when you go into this limit. But of course, I'm not saying that we have, yes.
May I ask, this was a critical gamma point, means that your collective motion of the center of mass of Fermi surface is gapless?
Exactly. It
means that your ground state has infinity. You can shift the Fermi surface, boost the Fermi surface without costing any energy.
Exactly. I can boost my Fermi surface without costing any energy. It's really like the center of mass as like a flat band now. It doesn't cost energy to the center of mass essentially to move it around.
So if you increase gamma to the unstable phase, what does unstable phase ground states?
Yes, I would. That's the next thing I want to say. But I saw a hand raised by Pavel, so maybe.
No, you said you will talk about it in the next slide. So go ahead. Sorry.
Yes, that's really the next thing. So now, if we allow gamma to become larger than 1, what happens is that you can take your Fermi sphere, you can shift it to infinity, and then you can lower indefinitely the energy of the system. So really the energy of the system in this case goes to minus infinity. So it becomes unbounded from below, and your system is really unstable. This is really what, by an unstable phase, I really mean the system losing essentially its well-defined ground state. So for gamma larger than 1, the system has no ground state at all essentially.
So, and this is I can think of my 2D surface that has a positive slope, critical slope, negative slope tuned by the gamma.
Exactly. So it's exactly what's happening. So you have a parabola where for gamma being from 0 being a half, it's positive. At gamma being equals to 1, it's really flat. And then at gamma larger than 1, it becomes negative. This is exactly what happens in the system. Okay. And this instability, so the fact that the parabola turns inverse, it is exactly what happens if you do not include the A squared term in the system. So if I do not include the A squared term in the system, I can still solve it analytically. But the change will be now that the coupling gamma prime, where now this is the coupling in the case where we do not have the A squared term, it is given by the ratio between the diamagnetic frequency and the cavity frequency. But of course, in this case, if I put really a lot of particles, because the diamagnetic frequency grows with the particle number, with the density, I can reach the situation where the particle density is just larger than the cavity frequency. And then in this case, I am really entering the unstable phase because my gamma prime has become larger than 1. So the conclusion from this is that if you really want to have a stable ground state for your condensed matter system, even for your simplest in the electron gas, you really need the A squared term there in order to have a stable ground state. And as long as you keep the A squared term, there is no superradiant phase and the system is really stable. And I would also like to say that the photon population in the ground state depends on the shift with respect on the origin of on the Fermi surface. So once the Fermi surface now it gets arbitrarily shifted in K space, also the photon population increases arbitrarily. So it is that you can directly get the fact that when you enter the unstable phase, you also have an infinite photon population. Okay, so this is like how these things are connected. And of course, what I told you now, it's all about the ground state. But the next thing that I would like to tell you is now what happens if we apply now an external electric field at time. Yes, Pavel?
Sorry, so with the A squared term, there is no transition at all, or the system is under control after the script?
So there is no phase transition as you keep the A squared term. That's the message.
So
there
you always stay in the stable.
You always stay stable. You always stay in the blue area. That's what happens, yes.
I see. Okay,
but
thanks.
Yes. Yeah.
So even in the stable case, what's the ground state mean value of the photon number?
Yes, let me go back to that. So in the stable phase, it is given by the difference between the renormalized frequency and the bare one. And this is approximately proportional to the electron density.
So the stable phase also has a photon condensation?
It doesn't have, so this photon population, it is finite. So the photon population per electron, it is essentially minuscule. It is microscopic. So there is no photon condensate. There is a finite population, but it's not macroscopic in order to call it a photon condensate, which is what happens in the decay model, for example.
So here is n photon is a total number of photon density.
Total number of photons.
So if you divide by area, the density is 0.
Exactly. Yes. So yes. So now the thing that I want to tell you is like, now what happens to the system if I apply an external electric field? Because I told you, okay, the fermionic state hasn't changed, but let's see now what happens in the transport process, which involves also excitations. So now I apply an electric field and I compute the corresponding current. And for that, I do standard linear response where the current density is related. It's proportional to the external electric field. And the conductivity, it is, of course, it has the Drude part and it has the current correlator. And the interesting thing in this setting is that in the current operator, we have, of course, the paramagnetic part, JP, which is the total momentum of the system, the paramagnetic current, but we also have the diamagnetic one. And now if you compute the current correlator, you have a non-trivial part coming from the diamagnetic part, okay? And because this ground state is a renormalized state of the photons for the field, this current correlator comes out to be non-trivial because of this finite photon population, okay? So this current yes, Pavel?
You mentioned there's a Drude contribution and current correlator. I thought that conductivity is solely determined by current correlator in this lower
left. It is a matter of how you define it, I would say. So some people include the Drude peak in the definition of the current correlator, some they don't. But this is the standard Kubo formula.
And there is also diamagnetic contribution because you have A squared coupling, right? So that
exactly.
Is that the first term in the bracket or not?
In which bracket?
In the lower left formula for sigma of omega.
You mean the n over m?
Yeah, n over m. Is it just because you have A squared coupling to vector potential?
What is n over m?
Yeah, you have E squared n over m, the first term on the lower left.
This, yeah, this
is the Drude part. Yes.
Okay.
This just comes from the total current essentially in the system. When you apply the electric field, it's just the expectation value of the.
Okay.
With respect to the external electric field.
This Drude part is will be cancelled eventually by the diamagnetic contribution at the static limit.
Probably, yeah. Okay.
So
thanks.
It will not be cancelled totally, but it will get modified. So let me show you there is a competition. There is a competition happening between the Drude and the part coming from the diamagnetic current correlator. Okay. And let me show you in this plot now what happens. So these two, they do not get completely cancelled, but what happens is that if you look into this plot, so the dotted line is the real part of the optical conductivity without any cavity. And the solid orange line is the one which has the cavity coupling. And what you see here is that the Drude peak at the frequency equals to 0, it gets suppressed. And it gets suppressed because what we have in this plot is that the part of the Drude weight has now been shifted into these new resonances, which relate to these renormalized bosonic excitations. Okay, so a part of the Drude peak gets now moved into these side peaks. Okay, and the key message here is that the Drude peak gets suppressed. So as you can also see in this formula, so sigma 0 DC is the standard DC conductivity of the electron gas, and now you see that it linearly decreases with the coupling gamma. Okay, and this can become visible when omega d, the diamagnetic frequency, and the cavity frequency, they are of the same order of magnitude. Okay, and let me say now from this formula, you can see that, for example, when I take the artificial broadening, I take it to 0. If my coupling gamma was able to reach unity, then the system from the system in the cavity, from having a finite Drude peak, which means that the system is a metal, would go to the situation where it has a 0 Drude peak, and which means that now you have turned it into an insulator. But because of this, of the A square term and the upper bound that the coupling gamma has, this cannot happen. So the system always stays metallic. And if gamma was able to go even larger than 1, then of course you would see that the Drude peak becomes negative, which again signals an instability in your system. Okay, so this condition of stability shows up also in the transport process of your system. Okay, but the key message from here is that the photons now take some part of the Drude weight and they distribute it into the non-zero part of the spectrum in these omega tilde frequency resonances. Yes, Pavel.
Could you repeat? So gamma cannot be larger than 1 because of this square term.
Exactly. So if gamma was able to become larger than 1, then the Drude peak would go negative, which would signal an instability.
But
right?
That could be a real parameter regime, but as you're saying, it's not a real parameter regime anyway.
It's not a real parameter regime.
Okay.
What the connection I want to make is that the stability conditions also show up in the transport. That's the key message I want to make. Okay.
So you mean the gamma can never be larger than 1? Is there any more fundamental reason, for example, gauging invariance?
So I don't have a deeper reason than just the fact that the A square term prevents you from that by renormalizing the bare cavity frequency. But I don't have any deeper reason, to be honest. It could be that gauge invariance is behind it, but yeah, I haven't looked at it from this perspective. But this is maybe an interesting thing because it could be like a sort of, it could be like a sort of generic proof about it. This is interesting, but I haven't looked at it from this perspective.
I think this needs to be looked into.
Yeah. This is definitely something very nice, which could be like a generic message about behavior of such systems.
Like no-go theorem, right?
Exactly. I agree. So let me then just summarize what I told you. So this is the first part of my talk. So I showed you the analytic solution of the system and the stability condition and relate the importance of the A square term. And I showed you like the cavity modifies the optical conductivity. So you get these new side peaks at the non-zero frequency of the optical spectrum, but you also get this suppression of the Drude peak. Okay. And if you have some further questions with respect to the electron gas, maybe this is a good point to ask them before I move on to the next part. If you don't, it's fine. Of course, we already discussed plenty of it. So
did you compute? Did you compute spectral function of single electron excitation? Something you would say measure?
No, this I did. This I didn't actually. I didn't compute the spectral function. I only computed the current correlators in this system.
So I guess it's probably should. I wonder if the quasiparticle residue changes from 1 or not. Is it in other words, is it a Fermi liquid or a Fermi gas?
So Pavel, you're thinking even in the non-interacting case, the quasiparticle residue can change.
Well, okay, let's ignore the effects of Coulomb interaction, but just because of the coupling to cavity, like how does quasiparticle look like? So just
Okay, so from the spectral function, if the residue is reduced, then we could one could tell whether it's a Fermi liquid or a Fermi gas, you are saying, Pavel. Okay, yeah,
Well,
I haven't looked into it.
interactions. Yeah.
It quantifies. Okay. This is interesting, but I haven't looked at it, so I didn't compute it.
Thank you.
But it's also one of the things, I mean, I have it for the output, but one of the things that I would really like to do is because we have the solution now of the Fermi gas, essentially, of the free electron gas, it would be nice to develop Fermi liquid theory out of this, because having this analytic solution can really help with that. But yes, we can maybe discuss more about it. So let me now come to the second part of my talk, which has to do with particles in a harmonic trap now, okay? Again, so this is again a relatively simple model. So we have charged particles with, it's better maybe to think them as ions like cold ions in a harmonic trap. So something like in a quantum simulator setting. And now you couple this system into a cavity. And we have two frequencies now. We have the little omega, which is the cavity frequency, and we have the capital omega, which is the trap frequency. And now the Hamiltonian of the system here, now I really take into account also the Coulomb interaction. So we have here the 2D part, the two-body part. And of course, we have the momenta of the charged particles. They are coupled to the photon field. Here, this is the external potential of the trap. And we have, of course, the energy of the photon mode. Again, I'm only thinking here for one mode. Okay. And as previously, the photon field is homogeneous and given by annihilation and creation operators. And the key observation in this system is that the A field couples, because it's homogeneous, it really couples to the total momentum of the system. So what you can do with this now is go to the center of mass frame in order to actually get the analytic solution of the system. So let me show you what I mean. So what happens if you go to the center of mass of the system? So this is capital R is the sum of the position of all the particles, and Rj is the relative distance of the particles with respect. I choose one particle and then I define the distances of all the others with respect to this one particle. What happens is that the Hamiltonian, because the forces coming from the harmonic trap, they are linear, and because the cavity field is homogeneous, the Hamiltonian separates into the center of mass part and the relative part. So the relative part contains all the relative degrees of freedom and the Coulombic part, but the center of mass is the one that contains the photon field. So what I'm telling you here is that the center of mass separates from the relative coordinates, and at the same time, the photon field also separates from the relative coordinates. And then for what this means is that all the photon matter processes and interactions really happen at the center of mass, happen between the photons and the center of mass. And so what you have essentially to solve here is two coupled harmonic oscillators. And let me just note that because of going to the center of mass, you get already this enhancement of the single particle coupling G naught by the square root n. So this is the first sort of collective type of behavior that we already see here, okay? That the coupling scales. But as I told you, the center of mass consists of two harmonic oscillators, and this we can solve then with a Hopfield-Bogolyubov transformation, okay, between light and matter now. So this is not a Bogolyubov transformation like the one before, in order just to absorb the photon, the A squared term, but this is now a Bogolyubov transformation between light and matter coordinates, okay? And then what happens is that you get two uncoupled harmonic oscillators, the D plus and D minus. These are now the polaritonic operators. These are linear combination between operators of light and matter. And we get these two mixed hybrid modes, omega plus and omega minus. And these are now really the polariton modes in the system. Okay, these are the hybrid quasiparticles that show in the system. And these two polariton modes depend on two parameters. One is lambda, which is proportional to the square root n to the number of particles in the system, and A here is just the area of the two of the cavity mirrors essentially. So this is the one tuning parameter that we have, and the second one is the ratio between the cavity frequency and the trap frequency. Okay. And now if we plot these collective modes, these polariton modes, because they are collective because they are really of the collective motion of the center of mass, if we plot them with respect to the relative cavity frequency, so the normalized cavity frequency with respect to the trap, what we see is that we have this upper polariton and this lower polariton. And when lambda is small, so it's 0.05, then you see that the Rabi splitting here is really tiny. But now as I increase my lambda by putting more particles, you see that the avoided crossing at the resonance point becomes larger. And then you see that also the polariton modes deviate for a longer period of frequencies from the bare excitations of the system. And if you look now also to how the two polaritonic modes, the energy difference of the two polaritonic modes, omega plus and omega minus, how it goes with the coupling, you see that the two here, they separate, they open up as I tune up lambda. And what you can find essentially is that omega plus minus omega minus, it is proportional to the coupling parameter lambda, which is proportional to the square root of n. So what the whole message of this plot is, this is the first, let's say, collective phenomenon that we see in the sense that the Rabi splitting changes as we put more and more charges in the system, okay? So the Rabi splitting can be really controlled by the number of particles, okay? And this is something that also shows up in these chemistry experiments, but it also shows up in these condensed matter experiments of electron gases, okay? This is something which is relatively known also from two-level models of quantum optics. So this is not that spectacular, but it is nice that we can get it from first principles, okay? And now the most interesting part is to look into the properties of the polaritonic ground state. So what I mean by polaritonic ground state, I'm talking about that of the vacuum state of the coupled system between the center of mass and light, okay? And first, very briefly, since I already told you about the photons, first I look into the photonic properties of the system. And for that, I compute the photon occupation and the photon correlation. So this is the Mandel Q parameter, which is essentially equivalent to the G2 function of the photons, okay? And this tells you what kind of correlations you have and whether you have correlations in your system. And here on the left-hand side, we see the photon population as a function of the coupling parameter lambda. And we see here that by putting more and more charges in the system, more and more particles in the system, the photon population increases. This is also something that showed up in the electron gas. But most interestingly, we see that the Mandel Q parameter, so the photon correlations, increase and they go above zero as we increase the light matter coupling. Okay, so let me tell you that the Mandel Q parameter, if I would have just a coherent state, it would be zero, which would mean that you just have a classical a state of the photon field without any correlations. But now, since it is positive, this means that we have bunched photons in the ground state, and these photons are correlated and they satisfy super-Poissonian statistics. Okay, the super-Poissonian statistics are equivalent to the statistics that also thermal photons satisfy. So there seems here to be some connection between strong light matter coupling and thermal behavior. Okay, and I would also like to say that there is also a third regime, a third type of statistic that show up between photons, which are called sub-Poissonian, and these relate to quantum light. So in this case, the Mandel Q parameter becomes negative, but this is something that here in the ground state doesn't show up. But we still have this non-trivial correlation between the photons. And now the next thing that we want to look at is like now on the matter properties. And this is the most interesting part, I would say. So what we do now is we take the polaritonic wave ground state wave function and we integrate out completely the photonic contribution. And then what we are left with is just the density profile, not the ground state density, but just the density profile of the center of mass. And what we find is that the density profile is a Gaussian, but the Gaussian now, if I would only have the system in my harmonic trap, the center of mass density would just be a Gaussian, where I would have here the bare mass of the system. But here now I have an effective mass, which depends on the two tuning parameters of the polaritons, lambda and gamma 2. And now if we plot this density profile of the center of mass, what we see is that as I increase the coupling, so I increase lambda and I stay in resonance, so light and matter are in resonance here, we see that the density profile of the center of mass is shrinking. So what this means is that this effective mass here is getting larger, and this is why you see sort of a localization of the center of mass, okay? And to appreciate better this phenomenon, we just plot here now how the effective mass behaves as a function of the relative cavity frequency. So gamma 2 is the ratio between the trap and the cavity frequency. And what we see here for different values of lambda is that at first the effective mass increases, but at the point where light excitations and matter excitations are on resonance, the effective mass gets its peak. So the localization of the center of mass becomes maximal when light and matter are on resonance. And this is something that also they see in these experiments in molecules, okay? So this is very interesting because you have a resonance effect, not in the excitation of your system, but in the ground state, okay? And this has been something that people have been trying to understand in this chemical setting for quite a while.
So you see something, say experiments, what is the precisely? It's the enhancement of mass or enhancement of localization?
So it is completely unclear to me, to be honest, what actually is going on in these experiments. But what the experimentalists say is that they can change how these chemical processes happen when light and matter are in resonance. And outside of resonance, they say that essentially almost nothing happens. So here I do not get a very sharp resonance condition, but we see that there is a maximal localization. So one way to connect in these experiments is that since the system since here the system, the mass gets enhanced, it means that the system sort of localizes more, so it becomes more stable. So in a sense, you can say that in a chemical process, then the molecules that come in this process, they become less reactive in a way. So that's the way to connect somehow, that the localization
it's
makes
just
the
an
system...
argument. It doesn't directly reflect experiments.
No. I'm not saying that. I'm not saying that it reflects directly to an experiment. All I'm saying that there are these three phenomena that show up in these experiments, that there is a ground state modification, there is a resonant behavior, and there is this collective behavior. And I'm just trying to say that with this simple model of charged ions in a trap, you can understand of them from a fundamental, let's say, perspective. I'm not saying that I can model an experiment with this, okay? Don't get me wrong. And now the question is like, how can we understand now this phenomenon in the single particle frame? Because what I'm telling you here is just how the center of mass of the system behaves. And this doesn't necessarily, does not directly or straightforwardly is reflected on the single particle frame, for example, on actual many-body observables like the density, the actual ground state density of the system. However, here, you have to remember that here we have n particles and they are interacting and they are also coupled to light. And to solve this system fully, analytically, it's essentially impossible. You can only do it numerically, okay? And even numerically, there are not many methods which can treat at the same time matter correlations, like two-body correlations, and also light-matter correlations. So in order to actually access the full many-body ground state of the system here, you have to find a way to go around this in order to implement some of your the methods that you already have, let's say, from standard many-body theory. So what we did in order to find an effective way, in order to understand what is going on in the grounds of the system, is the following. So as I told you, what happened to the system is that the localization of the center of mass density profile is shrinking. So this phenomenon can be understood essentially from a simple point of view, that what has happened is that the bare potential of the center of mass has now been renormalized, and you have an effective potential which now operates with this effective mass that we obtained before, okay? And this essentially, if you just replace this in your system, so if you put instead of VR, you put V effective of R, you will essentially just get the same density for the center of mass, okay? And now from that, if you take the difference between the two, you can actually find what is of course, the contribution coming from the cavity. So you can get what is the cavity induced potential. And now, if you write this potential, you go back from the center of mass frame to the lab frame of the single particles, what you see is, because this is the sum of the position of all the particles, you have a single particle contribution to your scalar potential, and you also have this bilinear interaction, okay? So now we see here that we have this increase in the single particle potential, and we have this two-body interaction, okay? So now what we can do in order to understand how the ground state of the full system behaves, without actually having to treat the photons, what we can do is just take the standard Schrödinger equation of just matter in this harmonic trap with the interactions, let's say, and put back just this cavity-induced potential and just find the ground state just using standard methods of condensed matter. Okay, and this is what we have now recently done. This is not yet in the paper, but will be in the revised version. So what we have done here is like to treat the system. So at first here, what I show you is just for the Coulomb part being equal to 0, in order to see just what is the effect of the cavity potential. But this is also one of the next steps that we want to do to compute also what happens with the Coulomb interaction and the competition between the two. And we consider here to have bosonic particles in 1D. And here on the left-hand side of this panel, we see the density, the actual many-body density of the system for different values of the particle number. So we go from 20 particles all the way to 10,000 particles. And what we see is that the density, as we put more and more particles, we see that on the sides, you are losing the density, weight from your density. Here, let me say that this is the difference of the coupled density from the uncoupled density, okay? So, and around the origin of your trap, you see that the coupled density increases. So what this means is that since the density around the origin of the trap increases, it means that the system is actually localizing. So we see that the many-body density shows the same type of localization behavior like we saw before for the center of mass, okay? And this is for a particular value of the coupling. So lambda over square root n is a fixed number. It doesn't change as I tune up the particles. And here on the right-hand side, now we see how the peak here behaves for 3 different values of the coupling. And we see now how it behaves as a function of the particle number. And the interesting thing is that in the red plot here is for the smallest value, 0, 0, 1, and we see that it follows a linear trend, but the increase in the density is very small. But as we go into larger couplings, we see now that in the green line, you go somewhere in between a behavior between linear and square root, and when I go to 0.1 for the coupling, you see that the density peak follows a nice square root n behavior as a function of the particle number, okay? So to wrap up this slide, what I want to say is that we see here from these mean field computations, but we have also done some exact simulation using multi-component time-dependent Hartree for larger number of particles. We see that the density, the ground state density of the actual system shrinks, it's shrinking, and we see this collective behavior. So we put more and more particles, and then this cloud is shrinking more and more. And this is also a signal for this collectivity that shows up in these experiments. And with this, let me summarize also the second part of my talk. So what I showed you for this harmonically trapped system is that the ground state of the system can be modified. We have this weak localization, this enhancement of localization by the cavity, which becomes maximal at the resonance, which is also a signal that shows up in these experiments. We saw that we have these pairwise interactions mediated by the cavity and this collective behavior in the ground state. So I put more particles and the effect on the total system gets enhanced in the ground state. And we also saw that we have these non-trivial photon correlations and occupations in the ground state. And as an outlook, the next things that we want to do together with Simos Mistakidis and Jose Sadekpour is now to explore further the impact of these cavity-induced interactions and to see actually what is the competition between the cavity potential and, of course, the two-body Coulombic interaction, and what happens to collectivity. Does it survive or it gets killed by the Coulombic part?
So also one question. Yeah. So I have confusion. You call this cavity-induced interaction. And as I say, it's just a center mass. You expand the center mass, you get a quadratic term, but it's not interaction.
Yes. So it is like a scalar potential for the center of mass, right? But now if you open it up in the lab frame,
yeah, but it's not interaction, right? It's just center mass dependent potential.
Yes, but for the single particles, you have this bilinear coupling. That's what I want to say. So
yeah, I think
it depends on which. So of your typical many-body codes, what they work in the lab frame. So if you go in the lab frame in order to do a many-body computation, this will be an interaction, because yeah, I understand what you're saying, that this sums up to a center of mass potential, but for your many-body system, for your many-body code, this is a mediated interaction. Okay.
Yeah, I still don't agree. Yeah.
Okay, I mean.
And also the mass. I know you calculate from your calculation, you find the mass enhancement, but you have a measurable definition of the mass. For example, why my question is why the mass enhancement is important? What's observable that is related to that directly?
Yes, of course. One is of course localization, but also if you would think now on the flow of the particles, if you apply some electric field or something, the effective mass, of course, is crucial for transport, for example, and for the motion of the system. So it is observable.
It's not very obvious how this effective mass enters into transport formula because this mass.
Yes, I agree with you.
Hybridization.
I agree with you.
Right. So there should be a definition of what is a mass based on transport or based on quantum oscillation. There can be different definition of mass. So why your definition of mass is crucial?
So I'm not saying it's crucial or something, but what I'm saying is that it has to do with how the spatial properties of the system relate. So if you would compute the variance of the position of the center of mass, so the variance on how much the position of the center of mass fluctuates, it is inversely proportional to m effective. This can be shown like exactly analytically. So the variation of the fluctuation of the center of mass around its origin, it's inversely proportional to m effective. Okay, right. So the larger m effective, the lesser the center of mass fluctuates. Okay, this can be this can be shown.
Mm-hmm.
And yes, and as an outlook now, so as I was saying, is like, yeah, I want to see what is the competition between V cavity and the Coulombic part, but also what is very interesting is to go to include like several species of particles, and then each subspecies will develop its own polaritons, and it will be interesting to see what kind of polariton interactions you have in this setting. And as for the free electron gas, a couple of things which are interesting to be done in the future is, as also Pavel said, that is to look into Fermi liquid theory in quantum electrodynamics using this exact solution of the electron gas. But also one thing that I am doing with Valentin Walter from ITAMP is that we are adding impurities into the electron gas and to see now what happens to transport and light matter phenomena around the impurity. And with this, I would like to thank you all for your attention.
Okay, yeah, thank you very much for the nice talk. Yeah, please raise your hand for ask your questions. Or you just unmute yourself, yeah.
Yes.
Could I return to one question I might have asked before? So that's about coupling to one mode, which is has some KZ and polarization in plane, versus modes that, for example, is polarized along X but propagates along Y. Okay, so there will be a continuum, and there will be a continuum of modes because you can imagine given your KZ mode, some KX, KY kit. I saw that you considered to some degree this case. So can you say what are the main differences? Is there any difference in the results when you consider this continuum of photon states coupling to your gas?
So when you consider this continuum of photonic modes, what happens is that if you look into the dispersion of your system by essentially because in a free electron gas, the curvature of the dispersion of the system, it relates, of course, to the effective mass of the system, right? So what happens in this case, as you put more and more modes, is that the effective mass of the system, which again is in this setting is rigorously defined by the curvature, it has a logarithmic increase with respect to the upper cutoff in the photonic spectrum that you show up, that you get. And another thing that happens is that the quasiparticle excitations of the Fermi gas, they also get modified by this continuum of modes. If you have only one mode, because you have a system in the thermodynamic limit, the energy of the electrons is essentially infinite, while the photons is minuscule, you cannot really modify these properties. But if you go into the thermodynamic limit also for the in the continuum limit of also of the photons, then you can have a finite energy density for the electrons and a finite energy density for the photons. And then in the thermodynamic limit, then you can actually start modifying some of the properties of the Fermi gas, like, as I said, the effective mass and the quasi-particle excitations and things like that.
But you mentioned that the effective mass has a logarithmic divergence.
Yes. Yes.
So
it grows logarithmically as a function of the cutoff in the momentum space of the photons. This is typical for quantum electrodynamics.
Yeah, I understand. But what cutoff should you take? I mean, should it be the lattice constant of the metal, or should it be something higher?
Yes.
And does it mean that actually, unlike the one mode approximation, you really can predict a strong reduction of mass for an electron gas inequality? This could be, I mean, if this is real, this could be a strong effect, isn't it?
Yes.
This logarithm is small for whatever reason.
So there are also, as we discussed, so before that, there are these stability conditions. There is an upper bound to the upper cutoff that you can consider, because after a point, if you include more and more and more, you run into instabilities and things like that. But it is unclear from an experimental point of view how many of these modes actually contribute to these processes. Okay, so I cannot tell you directly what would be in an experiment. Okay, because it's unclear experimentally how many modes are contributing, and it's also a little bit unclear whether the coupling really couples collectively, or the field fluctuation actually makes the coupling local, because if the field has a special profile, then it couples around this region in which it fluctuates. So these are still things that at the moment, we cannot address connect directly to an experiment. So it is still a little bit unsatisfactory on this regard, to be honest.
To reformulate the assumption that you have full translational invariance in 2D is probably not realistic for experiments. So just summing over all continuum states, that's why it might not make too much sense, because in real experiments, you have boundaries, you have inhomogeneities. And
exactly.
Is that your point?
So that's the point, that yet I would say that the model for the electron gas is not realistic enough, to be honest. So, but the key features you have to keep from this talk, I would say, is the fact that even with one mode, if it's strongly coupled, you can get an effect on the Drude peak. I cannot tell you whether this can be really measured in an experiment, unfortunately, because there are inhomogeneities, there are boundaries, there are size effects and things like that. But this is also why we want, for example, here now to include some impurities, because impurities, of course, are very important for transport. And so it's an ongoing process. I'm not telling you that this is definite or something. So
thank you. Thank you very much.
Thank you, Pavel.
Any more comments and questions? So if now, let's thank Vasilis again for this very nice talk.
Thank you, Jim. Thanks a lot for the invite. Also, we need to rearrange your talk at item at some point. So I stop sharing now.